Scientific investigations rarely end with a single experiment. In fact, the heart of science lies in the ongoing process of asking questions, gathering data, and using that information to dig deeper. It's not enough to simply collect data. We must be able to interpret the results, use them to generate new questions, and design more refined experiments. In doing so, we develop critical thinking and scientific reasoning skills that mirror real-world science. After completing a practical activity, we should ask ourselves, what patterns or trends do I notice in the results? Did anything unexpected happen? Is there something worth exploring further? For example, if we measure the time it takes for different concentrations of acid to dissolve a metal, we might notice that the increase in reaction rate begins to taper off at higher concentrations. This leads to the next question. Is there a concentration limit after which no further increase in reaction rate occurs? That new question can then become the basis of another investigation. By thinking critically about what the data suggests, we begin to see the investigative cycle, where one experiment naturally leads into another. To design a meaningful experiment, we must learn to identify and manage variables. Variables are the building blocks of experimental design and influence the reliability and validity of an investigation. The independent variable is what is changed on purpose, for example, light intensity, temperature, concentration. The dependent variable is what we measure in response, for example, plant growth, reaction time, volume of gas produced. Controlled variables are all the factors kept the same to ensure a fair test. Clearly identify these variables and explain the relationship between them. For instance, as the temperature increases, the independent variable, the rate of reaction, the dependent variable increases because particles have more kinetic energy and collide more frequently. To ensure the results are valid and not influenced by unrelated factors, we must also identify the variables to control. For example, when investigating the effect of temperature on yeast activity, controlled variables might include the volume of solution, the concentration of sugar, and the type of container. The hypothesis is a testable statement that predicts the outcome of the investigation based on prior knowledge or observation. A good hypothesis should clearly link the independent and dependent variables and provide a reason for the predicted outcome. It can use the familiar structure. If change in independent variable, then change in dependent variable because scientific reasoning. If the concentration of salt increases, then the boiling point of water will rise because salt ions disrupt the water's ability to evaporate. Writing a clear hypothesis helps us focus the purpose of the experiment and sets us up for effective analysis later. Designing a practical method involves making a testable procedure. Think carefully about how you will manipulate the independent variable, measure the dependent variable, and maintain control over other influencing factors. A good method should describe 1. How to change the independent variable. Systematically alter one factor. For example, using different concentrations of a solution, adjusting light intensity with lamps, or changing the mass of a reactant. 2. How the dependent variable will be measured. We must describe exactly what we will measure, in what units, and how often. This might involve using stopwatches, thermometers, scales, or other scientific tools. We should consider the precision and reliability of their measurements, for instance, measuring to the nearest 0.1 mil instead of 1 mil where possible. 3. How controlled variables will be kept consistent. Describe how to ensure controlled variables stay constant. For example, using the same equipment, measuring with the same instruments, or performing all trials at the same time of day to avoid temperature fluctuations. 4. How data will be collected and recorded. A plan for data collection should include repetition, tables for recording, and strategies to ensure reliability, for example, taking the average of 3 trials. We should consider how we will organize the results to make analysis easier. 5. How risks will be managed. Risk assessment is a key part of any practical. Identify potential hazards, for example, glassware, heat sources, chemical exposure, and describe clear steps to reduce risk, such as wearing safety goggles, using gloves or tongs, handling hot equipment on heat-proof mats, disposing of substances safely. The beauty of science is that it's a process, not a one-off activity. By treating primary data as more than just numbers on a page, as something that can lead to further questions, students engage more deeply with the scientific method. They learn that science is evolving. Each observation leads to new questions, and each experiment is a stepping stone to deeper understanding.